Because of high amounts of solutes that are reabsorbed from here, that first goes into the interstitium, the medullary interstitium becomes highly hyperosmolar, like the osmolarity changes here. It was 300 before, now it would become 400, now 600, 800, like 1200. When fluid reaches here, it finds that the medullary interstitium is highly hyperosmolar, so it also want to equalize this hyperosmolarity. So it also equalizes this hyperosmolarity by again losing much amount of water, because this complete part is water permeable, and then this system is repeated again and again in order to equalize the whole system here of this watertight system and water permeable and impermeable system. This system is repeated again and again in the loop of Henle. So this complete system is known as the counter current multiplier system. Now another system comes, that is the urea cycle in renal medullary area. This part, this whole complete part, this is urea impermeable. Only the last part, this is urea permeable, and now some of the urea leaks out and then comes into the hairpin and into the thin descending part, and then again it filters, and again this complete part is impermeable. So this also contributes, because urea first enter into the interstitium, then it is reabsorbed into the hairpin turn and loop of Henle. So it also contributes into some of the hyperosmolarity in the medullary region. Now the last part, that is the vasa recta as counter current exchanger. In this part, there is vasa recta in the renal medulla. In this part, the blood flow is really slow. Because of the slow blood flow here, it doesn't allow us to wash away most of the solutes, and this also contributes into the medullary hyperosmolarity. Now comes the last part, that is the ADH. In the presence of ADH, water here is reabsorbed, and this results in highly concentrated urine. But in the absence of ADH, the last part is impermeable to water, so highly diluted amount of urine would be passed. That's all